Hi everybody, I'm Alexandru Nedelcu. I'm a software engineer from Bucharest, Romania. If you want to know more about me, that's my Twitter account. I spent way too much time on Twitter. That's my website, personal blog. And I'm working for L'Oreal. If you're ever in Bucharest, come and say hi. We are friendly. So today I'm going to talk about Monix. Monix has been my hobby for the past several years already. It's a Scala.js library for composing asynchronous programs. It exposes a bunch of useful high-level abstractions for working with asynchrony. It's a type-level project, which means for you it means that it adheres to certain quality standards, let's say, plus it interoperates well with the rest of the ecosystem, and it's currently at release milestone, release candidate 1. Release candidate 2 is a little delayed, but is going to be released in the following week. So, and this version 3 that is going to be released soon, it's a major version introducing lots of goodies. So version 3, it's about deep integration with type-level cats, which is the new standard library for functional programming in Scala. It introduces the iterant data type, which is for lawful pool-based streaming, and I'm going to talk about it in the second part of this presentation. And it contains major improvements across the board. The project, as a little history, started in 2014, and it was originally called Monifu. And it was developed because I had a need for developing software that controls and monitors power plants. It was inspired by Eric's Java. I was actually inspired by that reactive course on Coursera, which I didn't like so much as the functional programming course, but I liked Eric's presentation on the subject. And I renamed it to Monix on December 13th the following year. And I have to mention, strange things happen to me around New Year's. I mean, like, every year I have like this existential crisis where I become suddenly productive on GitHub. And if you're ever wondering from where the logo is coming from, it's a combination of Scala's logo plus I'm a cheap bastard, and I made it myself in Inkscape. So yeah, this talk is about streaming approaches, and this image should be a metaphor for, you know, how the information is flowing. It's supposed to convince you that I know what I'm talking about. So, push-based streaming, this is what Observable is about, and it was its origins are in ReactiveX, also called Reactive Extensions, and it was introduced by these fine folks working for Microsoft, out of which Eric Major has always been an inspiration. And the basic idea is that starting from the basic iterator and iterable pattern, which has several problems, like it's synchronous. You cannot describe asynchronous processing with it. It doesn't close resources. And it has a pretty dirty protocol, let's say. We can actually flip it around and convert that to a push-based abstraction. So in our case, we no longer have the iterable as a factory. We've got the observable, which receives a subscriber that gets subscribed to events. And then the observer starts receiving events on next, on next, on next, until a final event. And the stream can end in either in success with a non-complete or in error, and it receives like an error. So this diverges, by the way, from the traversable in Scala standard library. Traversable, due to its interface, it has an implicit contract in it that it cannot describe asynchronous streaming, because there's no way to know whether the stream ended or not. But Observable has like a very explicit event in it that, okay, the stream is now complete. This interface too has problems, like it has no ability to do back pressure. We'll talk about that in a moment. So if you think about state machines, as I said, you receive on next events until either on complete or on error happens, or until the early cancellation event happens from the consumer side. Although in the original rx.net specification, cancellation is a little unwieldy because you have to work with forward references. Observable is the dual of iterable, or you can think about it as its evil twin. Eric Major is fond of saying that. And so as I said, problems. Whenever we've got a push-based streaming approach like that, the problem is that we've got no protection against slow consumers and fast producers. And we also have these problems when we work directly with akka actors. So when doing that, you either have to implement throttling, meaning you start dropping events on the floor whenever your internal buffer fills up or whatever, or you come up with a sane sampling strategy. But the thing is that the buffers are essentially unbounded because you don't have a protocol in there that does back pressuring. On top of vectors, you can implement it yourself, but it's kind of unwieldy. So as a piece of trivia, Flatmap in the original rx.net specification is alias to merge map because concat map, which is like the monadic bind that we know from Scala standard collections, the concat map is unsafe because it uses unbounded buffering, so your process can blow up with an out-of-memory exception. And as an alternative, the folks at Lightband came up with the Reactive Streams protocol, which kind of resembles that, but introduces a protocol for back pressure. Basically, you receive a subscription with a request in it, and then you start, the consumer has to communicate demand to the producer, give me the next 10 elements, give me the next 10 elements. And the producer is bound by that contract. If you read the Reactive Streams specification, it's kind of a low-level protocol because there are all of these weird conditions, what happens in the presence of errors, what operations are supposed to be concurrent or not, and so on. So it's basically for library authors, it's not for users because we've got better things to do. But the libraries can implement reactive streams for interoperability, so it's great for that. Before reactive streams was a thing, however, I had the idea to work with in that protocol to introduce future from the standard library for implementing back pressure. So the idea is that on next can return a future event, and then the producer is bound by the contract of waiting on that future for sending the next element. This is sort of a mixture between a pull-based and a push-based approach. It's still push-based. It's a little hard to explain why, but it works well. And the second idea I had was to introduce consumer-driven cancellation, which is, okay, it resembles reactive stream, the reactive streaming stuff. So instead of working with a future unit, we can work with a future of acknowledgement, the acknowledgement being a simple enumeration that tells the producer continue or stop. And this is basically the full protocol. There are some low-level details in it, like what happens with the final on-complete event, is it back pressured or not. But as you may notice, this is like it's still like a very impure low-level protocol. I guess that if you love working with akka actors, you can also love this, but basically you have to rely on shared mutable state, and it's kind of low level, but the observable, just like akka streams, the observable is a high-level data type, and all of those details are properly encapsulated, so you don't usually have a need to work with that low-level protocol unless you really need it. And observable is basically behaves like a lazy collection, like a Scala collection, but a lazy one that can suspend side effects and do all sorts of neat things, do all sorts of aggregations and throttling and buffering and so on. And usually you work with it like with high-level operations that describe the processing that you want to do with pure functions, let's say. And in order to execute an observable, in order to execute the described computation, you have to subscribe to it. Subscription is still a low-level operation, so what we are doing is to also provide operators, fold operators that return tasks instead of having to do subscriptions. Task is a high-level data type that represents basically the I/O monad from Haskell, but it's in Scala and it's concurrent and it's great. And it also interoperates well with Scala's future. There's a cancelable future in Monix, but it interoperates with Scala's future because it inherits from it and it works properly. And if you ever feel the need for a cancelable future, we've got one in Monix. Well, it's actually in Monix execution where all the dirty stuff goes. So observable is a monadic type. Our Flatmap is the monadic Flatmap. It passes all the laws because it's lazy and it suspends side effects. This is an example where we are reading lines from a file, but this describes what we call a cold data source, meaning that you have to subscribe to it in order to read that file, because just calling the function won't do anything. And if you are familiar with the I/O data type or with task from Scala, observable itself is I/O-ish. It doesn't need an I/O or task to evaluate, and this is an important point which I'll talk about in the second part of the presentation, where I'm going to talk about iterant. So what is observable great about? It's great about doing reactive operations, like for example switch map, which is a really concurrent operation. I would probably need a whole talk to describe what you can do with switch map because it's such a powerful thing. But you basically can describe, for example, a debounce, which is already provided. Debounce, sampling, throttling, echoing the last element in case the source goes silent, and you've got variations based on that, like in case the source goes silent, start repeating the last event. And all of that makes it easy to build a pipeline of where you process events coming from real-time data sources, like what we did when we were monitoring power plants. So yeah, this is an example where we filter out the repeated elements from the source. We are sampling those events every 1 second. Like, I mean, don't emit events for more events than one every second. And then if the source goes silent, repeat the last element every 5 seconds. So it has a lot of powerful operations like that. And I'm not going to talk about this one. The observable optimizations. I did a lot of work in optimizing observable. For example, Flatmap as a case study. It models a complex state machines for eliminating basically asynchronous boundaries from it, because those are bad for throughput. It deals with concurrency by means of one atomic, with cache line padding, and using get and set platform for intrinsics. And I really encourage you to look at the Monix execution subprojects, because I've got a lot of really low level concurrency abstractions in there. And we are also using like this awesome library known only by library authors called JC Tools, exposing really fast concurrent queue implementations, because we've got scenarios where we've got multi-producer, single consumer. We've got such scenarios, so it's those implementations are way faster than what you can find in Java's or Scala standard libraries. So as a consequence, observable basically has best-in-class performance. It competes with every other library. It's not the best when you are doing benchmarks. You basically optimize for the things you care about, and I mean that's what authors will show you, the things they cared about, but performance is pretty good overall. And it provides referential transparency, and it's one of those cases where the API is pretty much pure, but it has dirty internals, which is an interesting approach. I mean, coming like me from the Java side instead of coming from the other side, from Haskell, let's say. This is in contrast with the other approach, right? So right now, let's talk about pool-based streaming. And Iterant is another alternative introduced in Monix in its own sub-project. And it's meant to model a purely functional, pool-based approach. Goethe is known to have said architecture is frozen music, which inspired John Bentley to say that data structures are frozen algorithms. You may know John Bentley as the author of the Programming Pearls book. And the key insights in designing FP programs that I learned the hard way, because it's one of those things where you have to learn by stealing the trade from others, is to, when designing an FE program, you have to think about freezing algorithms into immutable data structures. You have to think about state machines most of the time, and you have to be lazy. And how can you be lazy in a strict language like Scala? Well, you turn simple values into functions, and you suspend side effects in I/O or task or whatever. So this is the part where I start talking about state machines, because I have a real fetish for it. We can start by from the Scala standard list, which is basically what they call an ADT. A list node can be either a cons, like a combination from a head and the rest of the stream, or a nil, which represents the empty list. So this is like a really simple state machine, by the way, because in order to consume the whole list, you have to process the list and follow the tail element until the end, and then when you're at the end, you're done. So we could say something like this. We are already renaming it to iterant and replacing that rest of the stream with a lazy function, because we want to be lazy. And we can have errors because we have functions in it, so it's not like we can have an eagerly evaluated list anymore. So because that's a function, you can throw an error. Well, we need some way to represent errors without actually throwing them, because throwing errors is not cool. So this is a state machine, and the end conditions are halt, error, or halt, none, which represents success. And let's say that we want to do resource management, and this is a problem with something like Iterable. So if we want to do resource management, we present the user at each point with the option of doing an early termination by introducing a stop function in that data structure. So at each point of the processing, the consumer has the choice: does it go for the rest of the stream or does it stop? And based on this, you can implement resource safe, let's say, operators on top, like take. If you do a take 100, let's say, from an iterable, an iterator, it's not going to be safe if that iterator goes over a file, because it's going to leave the file handle open, and that's not what we want. And because we are lazy, we are going to introduce another state called suspend, which doesn't have a current element, and it allows you to defer the rest of the processing until later, let's say. So, or it allows you to eliminate elements from the stream. This is what suspend does. So right now we can have, like in the stream, next suspend, let's say, until the end of the stream, which can terminate either in halt or in early stop. This is a state machine. And how do you work with this? You build an interpreter for it, and let's say, I mean, like FP developers, you start doing pattern matching like crazy. So to implement a filter operation, you do pattern matching on that stream. If it's empty, you return empty. If it's a suspend, you return a suspend by creating a closure here that applies filter to the rest of the stream. As you may know, in Scala, this is not stack safe and it will blow up, but we can solve that. And we can say, okay, if we have an next and it satisfies the predicate, we can return it, but apply filter to the rest of the stream, otherwise suspend. and we've got a filter operation defined. That's not stack safe, of course. Scala has problems like that because it's an eagerly evaluated language, great for performance when you're dealing with mutable stuff, not so great for functional programming. So what we do in Scala is to start working with trampolines or with execution contexts. So we could say, let's work with future, and future has a stack safe flat map because it pushes those runnables in the execution context. But future is not a function, and we need functions. I mean, this stop here would be useless if it were for a future unit. We need a function in it. We could turn that into a function. I mean, this is called a thunk, a parameterless function that on evaluation returns a future, and this would work. But we already have a task in Monix, and it's a fairly performant task, and it has a memory safe flat map and map implementations, and we can work around the need for that. And task is a function. I mean, you can consider it as being a function with which you can describe side effects, so that works. Or we could work with coeval. Coeval is a data type in Monix that's like task, but it guarantees synchronous execution. Or we could work with the new cats effect IO. I mean, like, do we really have to choose? So we can start playing in the big boys league and do parametric polymorphism and introduce an F. We say we want to, work with any F. And the interesting thing about it is that the actual restrictions about what F is comes on the operations themselves. So in this case, we are saying F must implement sing, which is like a type class described in cats effect that says this is a monad that has a memory safe flat map and that can suspend side effects. With that law, we can describe chaining in our streaming, and we will be safe in the knowledge that it won't blow up. It won't blow up the call stack. It will be safe to use, let's say. So now it works for I/O, it works for task, it works for coeval, and iterant, again, it's a high-level data type. That pattern matching I just showed you, you don't really have to do it because it already provides operators that you could use, just like Observable. It actually provides many of the same operators, except that the concurrent ones are really harder to implement than with a push-based approach. So, but we are getting there, and the current version is already really useful, even without switch map and throttling and so on. And you can work with I/O, you can work with coeval, you can basically shove anything in there that implements sync. And this construct right here is called partially evaluated type. Basically, you're doing like a trick with apply. Don't be scared by it because it's nothing special. It's like a trick we are doing for the builders, let's say. But it's yeah. So it has performance issues, like all things in Scala that are too pure. The problem is that it's basically a linked list. Linked lists are terrible for performance, and it's a linked list that introduces lazy or asynchronous boundaries at each step, and those are terrible as well. So in order to make stuff more performant when working with functional programming, we really need to find ways to work with arrays and to avoid essentially lazy asynchronous boundaries. So what we can do, I don't know. What can iterate over arrays efficiently with like near zero performance? Well, if you ignore the boxing they do. If only we had such an abstraction. But, what if we introduced in our internal state nodes that wrap iterables and iterators? Well, now we can shove arrays in them and process stuff in batches. So instead of introducing lazy or asynchronous boundaries that need to be evaluated at each step and which are slow, you can simply stream stuff in batches. And I'm going to be honest with you at this point, this is no longer a purely functional data structure. I mean, it is in spirit, but not in actual implementation, because it has an iterator in it. But because F can suspend side effects, that doesn't matter for the operators, because the operators are meant to suspend the are meant to be referentially transparent. So whenever we've got processing that triggers side effects on iterators, those get suspended, and in turn you achieve performance. And now I'm going to do a comparison between iterator and iterant and observable. And as a really cool case study would be the implementation of Scaneval. Scaneval is like the essence of reactive programming with ReactiveX. Scan, actually, not Scaneval. Scaneval, I think it's an innovation in Monix. But as a really cool case study, I implemented it for both. And this would be like the signature for iterant. It has a sync restriction in it. And you don't have to understand the implementation, but this is pretty much the gist of it. I mean, it's like a recursive function that basically does pattern matching. There's nothing special about it. The cool thing is that mere mortals can do this. On the other hand, for observable, we introduce an effect restriction because observable does evaluation by itself. Effect being larger than sync, being a subtype of sync, and it's more restrictive. And effect basically represents the ability to evaluate an effect. So observable needs this because it can no longer defer that evaluation to the underlying effect. Not sure if you understand this, but it's a really cool trade-off to make. And the implementation is actually specialized for task, and then we convert from effect to task. I think we can, with the new additions to Cat's effect, I think I could describe Scaneval entirely via the type classes in Cat's effect, but right now it's specialized for task actually, and we are doing conversions. And the thing about observable scan map is that its implementation is essentially that of Flatmap. And I mentioned Flatmap on observable before. It does like really weird stuff internally to achieve performance. To get rid of asynchronous boundaries, you have to be like a concurrency guru for the JVM to do that. And I'm not that. I mean, I'm still unsure if the implementation is correct. I can only say that it's correct because I've ran a lot of tests on it, but because it deals with Java's memory model, with concurrency rules related to Java, it's really hard to reason about it. But on the other hand, the implementation for iterant is something that's understandable. So to do I did a bunch of benchmarks, and the blue and the orange lines are observable. So blue is flat scan, observable is Scaneval, and the gray bar is Scaneval and from iterant. And iterant is only decent because I did that optimization with Iterator. So by being able to stream stuff in batches, we can apply optimizations there. The performance is less, but it's still decent. And you can pretty much say about it that observable has performance, but iterant has reason. And depending on the use case that you have, you make that trade-off. Do you want performance or do you want reason? Well, observable is useful for reactive stuff, as I told earlier. But this is another benchmark showing the performance impact of doing stuff in batches. This green bar right here represents iterant that operates with batched iterators underneath with batched arrays, basically. And this one is without, so the performance implications can be quite huge. And this blue bar is the throughput of observable, which exceeds both. So when analyzing the differences between them, one interesting thing is that observable cannot have a ThirdRight operation on it described. ThirdRight. I'm not sure if you're familiar with it. In Scala standard collections, it's not exactly right because ThirdRight is supposed to be lazy such that you are then able to short circuit the processing. It's not actually the ThirdRight that we want, but it's a pretty cool operation. It's not possible for observable because observable is not a recursive data structure. You basically need something to be pool-based in order to describe a ThirdRight for it. We can work with substitutes like fold while left L, which I came up with. But iterant can have a ThirdRight. It's not exactly the signature that you get in Haskell or in Scala because you need a cancellation token to be in there. Otherwise, this resource handling cannot be automatic. In this case, you basically need to leave the user in charge. So in case the user short circuits the processing, it needs that cancellation token to close the file handlers and so on. And it's a really powerful operation. You can describe something like exists with it. So it would short circuit the processing. If the predicate is satisfied, it does a stop, which releases resources followed by true as a result, or similar for all. We can even describe a memory safe concat operation for it, although we don't really do that because we care about performance implications. So concat has its own implementation, but we could do this and it would still have useful characteristics. And this was an embarrassing Twitter moment for me because I was kind of pissed off that I couldn't implement ThirdRight for observable, and for iterant I finally realized eventually that I need a third parameter. The thing is that a ThirdRight operation needs to reflect the shape of the data constructors. It's what they call the catamorphism. It's really powerful stuff, and we can describe it for observable. So, in conclusion, observable is best for reactive operations, shared data sources, of which I haven't talked about. I mean, it's really good of splitting an operator in two and applying batching and back pressuring there, throttling, buffering, performance. And iterant is best for easier implementation reasoning, and basically sometimes, I mean, you have like a sequence of I/O or task operations already defined and you want to make that into a stream. So why not use an abstraction that does that naturally, because with observable it's kind of a stretch. And both implement the Reactive Streams protocol, which means they have interoperability with other streaming libraries. I mean, you can take an observable on an iterant and consume it with a pipe from Akka Streams, or you can take Akka Streams data source and consume it with Monix consumer. So, and both do back pressuring and safe resource management. And one more thing in my work, I noticed that when you import abstractions from Haskell, they usually suffer from performance issues because the developers want elegance in implementation. I'm saying screw elegance in implementation. I mean, if it's properly encapsulated, you need to achieve a good throughput such that the user doesn't have to worry about it. The user can then worry about it, can then worry about their own business logic or whatever. So performance is not important, but it's usually not important in applications, not in libraries. So if you allow some impurity that's properly encapsulated, like cool things can happen in Scala libraries. Anyway, so that was it. I think we have some time left for questions. Oh, by the way, the website has a lot of documentation in it, and more is coming. And you can follow the Twitter account or the organization on GitHub for news and announcements. And we've got a friendly Gitter channel that I forgot to mention here, if you want to chat about it.
Okay, great. Yeah, we actually have 10 minutes for questions. So who wants to go first? I come there and then there.
Could you say how Iterant really compares to FS2 streams?
Yeah, at this point, Iterant has fewer operations defined because FS2 has been developed for longer. As a difference, Iterant is a lot more explicit in its internal encoding about what I said, finalizers, about stop. And you can actually work with its internal encoding. You can understand it. The FS2, on the other hand, tries to be smarter about cancellation, because their priority was to describe concurrent operations that are more naturally described with observable, let's say. I think right now Iterant has the simpler implementation. I have no idea how that will evolve, but it's basically another exploration of the design space, let's say, if you take a look. I think yeah, I'm not sure what to say there. They are similar in approaches, but not in implementation. Iterant has a simpler implementation, but at this point also does less. So, but there's virtue in that, in being simpler and doing less. I want to introduce a merge operation, for example, but on the other hand, I'm not sure if it's worth it, because if users want to do merging, Observable is far better for that.
Yesterday there was a talk, I think, in the same room about GraalVM, where the speaker presented quite impressive performance gains, particularly on the highly polymorphic kind of functional code. I wonder if you try to run, Iterant on GraalVM and how numbers compare, if you have.
No, but it's an awesome development. I'm really excited about it. I've heard about it. So they are doing better escape analysis, and they can get rid of short-term allocations much more efficiently. I hope to try it out soon, but I haven't. So it sounds really cool.